In this video, I'm going to talk about an experiment that we might do in the lab, and we will hopefully do it in the lab at some point. And the experiment will be this reaction. So we would do most likely magnesium plus hydrochloric acid. Oops, EQ. And you know that a metal plus an acid is going to give you a salt, and my salt is going to be magnesium chloride. Now magnesium is in group 2, so it's Mg2+. Chlorine is in group 7, so it's Cl-, so it must be MgCl2 plus hydrogen gas, H2. That needs to be balanced, and to balance that we need to have a 2 there. So what we are going to do is, oh dear, that shouldn't be AQ, that should be gas, obviously. So what we're going to do is we're going to measure the amount of this gas produced. We're going to measure that. And we're going to remember that the rate of reaction, so you'll remember from the last video that we had, here we had the amount of reactant used divided by time taken, but I did tell you that you could do it either way. You could do it with the reactants or the product. So now our rate of reaction is going to be not the amount of reactant used, it's going to be the amount of product made. Divided by time taken. Okay, so in order to do that, we need to have a way of measuring this amount of gas, because if I do this reaction, let's say I have a conical flask, and in here I've got some HCl, and I add in a little bit of magnesium, that's my magnesium, then you'll see some fizzing, you'll see some bubbling around the magnesium, and the gas will come off and it will escape, and you won't be able to measure it. You won't know how much you've got. You know, you need to be able to measure the amount of this gas being produced. But if it's just going into the lab, into the air, then there's not much you can do with that. Okay, so we're going to use an experimental setup that looks like this. Okay, so you can see here that I've got the same thing in my conical flask. I've got my hydrochloric acid and I've got my piece of magnesium, but I've got a special kind of conical flask with a sidearm on it. And to the sidearm I attach a gas syringe. So it's like a normal syringe, but it's a bit bigger. All right, you know, it's not the kind of syringe that you'd use to inject some kind of drugs or some kind of medicine into yourself. It's quite a big, hefty gas syringe, and I'll be able to show you one when we get back to school. All right. And what happens is as the gas is produced, it comes up here, and then the pressure forces the syringe to expand. Okay, and it pushes the arm out. All right. So normally, when you were injecting drugs, you would push this way, and it would force whatever inside the syringe this way. Whereas now it's going the opposite way. So the pressure from the hydrogen that's produced pushes this way, and it pushes the arm out. All right, and there are markings on the syringe that allow you to measure the volume of gas that has been produced. Okay, so you need to be able to draw that kind of experimental setup. So you need to have a sketch. It doesn't need to be very artistic, but it just needs to be, you know, a small diagram. Looks like this. You need to have a stopper there to stop any gas going anywhere else, and your sidearm, and then your syringe. And if it looks like this, it's fine. Okay, and it has to have gratings on it. Okay, and we would label that here as a gas syringe, and this would be a sidearm flask. Okay. Now, same as before, in here you have your HCl and your magnesium. Okay. And you're producing your H2 into your gas syringe. So let's now suppose that we do this and the reading at the start is 0 centimeters cubed. Okay, obviously because it's going to be all the way pushed in. All right, and then let's say we do this, we put the magnesium in and then we leave it for 30 seconds. And then the reading after that 30 seconds is, let's say, 50 centimeters cubed. What is the rate? So the rate would be the amount of product made. So we've gone from 0 to 50 centimeters cubed. So it's going to be 50 minus 0 divided by the time taken, which was 30 seconds. So we have 50 divided by 30 is 1.67 centimeters cubed per second. So this reaction would be producing 1.67 centimeters cubed of hydrogen gas every second. Okay, and so I can then ask another kind of question. I could say, well, let's suppose I do this for 2 minutes. How much gas would be produced? In 2 minutes. Okay, and you might want to have a go at that question now. If you want to have a go, pause the video. All right, so how much gas would be produced in 2 minutes? Well, 2 minutes is 120 seconds. And I know that I'm getting 1.67 centimeters cubed every second. So I would get 1.67 times 120. And that would give me times 120, it would give me 200 centimeters cubed. Okay. If you got 200.4, then it's because you were using 1.6. I didn't use 1.67. I used 1.666666 because that's the actual value of that. Okay, so when we did this reaction, we took the reading at the start at 0 seconds, and then we put the magnesium in, and then we waited 30 seconds and took a new reading, what, 50 centimeters cubed. Now, when we do this for real, we won't do it like that. What we'll do is we'll take a reading every 10 seconds, let's say. We'll take a reading at 0, then at 10, then at 20, then at 30, then at 40, then at 50, then at 60. And then we'll plot a graph. Okay, so what we'll do is on the horizontal axis, we'll have the time. And on the vertical axis, we will have the volume of gas. Okay, and the time will likely be in seconds, and the volume of gas will be in centimeters cubed. Okay, and we'll have this data in a table. We'll collect something like time and volume. All right, and it might be 0, 0, 10 seconds. There might be, I don't know, let's say 12 centimeters cubed, and at 20 there might be 22 centimeters cubed, that kind of thing. All right, and we'll plot this data in this graph. Now, we're not going to worry about plotting graphs now, okay, because it's a bit difficult to do that remotely. We'll do a lot of graph plotting when we get back. But generally, when we do this, you'll notice that the kind of graph that we get will look like this. Okay. So there are a few important things that you need to know about this kind of graph, right? And they are as follows. All right. Here at the start, we have a steeper gradient. Okay, so you can see that the gradient here is quite steep, and then here it's not so steep. Okay, and that's what happens as the reaction goes on. The steepness of the gradient decreases, so it gets less steep. Okay, so at the start we have rate is fast, so the gradient is steep. All right, so that's number one. That's the first important thing you need to notice. The second important thing, as I just alluded to, is as the reaction goes on, okay, so number two is as reaction proceeds, rate decreases, gradient becomes less excuse me, less steep. Okay, so you can see that if you think about it, let's say we take a certain time interval. Let's say we take, if I get my ruler, let's say I take a centimetre worth of time. Okay, this amount of time here. If I extrapolate up, so if I go up here, I've got about this much volume of gas has been produced. This much volume of gas was produced here. All right. Let's say 1 centimetre is 10 seconds. Let's say that's 10 seconds. I get 2 lines worth of gas. All right. Now, let's say I do the same over here. Okay, so I'm going to use 1 centimetre again. 1 centimetre. And if I go up from there, you can see that I'm here and here. So I've only produced this much gas, but it's the same amount of time. It's the same amount of time, but the amount the graph has gone up by is much, much smaller. So the rate is decreasing. I'm producing less gas as I go along. All right. Now, if you didn't quite catch that, you just pause the video, go back and watch it again. All right. But so that's number one, number two, and number three is here. Okay. After a while, what will happen is you'll be doing this experiment, and the gas syringe will be pushed out until eventually it will just stop moving. All right, and that will coincide with when the magnesium stops reacting. Because once all the magnesium is used up, this is all gone. We can't make any more hydrogen gas. So the gas syringe won't be pushed out anymore, and the reaction has stopped. So we know the reaction has stopped when this line goes flat. Okay, so at the finish, rate is 0 and the line is flat. And the line has to be flat because the volume isn't changing. We're not producing any more gas. So as the time carries on, our amount of gas produced isn't changing. Okay, so those are the three important things that you need to know about this kind of graph. So you need to be able to analyze that graph. So if I were to give you a blank version of that graph, you'd be able to say, yes, well, you can see that the gradient here is steep, which means it's fast at the start, and then the gradient gets smaller, which means the reaction is slowing down, and then here, where the line is flat, it means the reaction has stopped. Okay, all right, very good.